Thank you very much for coming, everyone. For those of you who don't know me, my name is Ben Evans. So I'm one of the co-theme leads, along with Mark Whitaker, who's in the room somewhere, looking after the materials and manufacturing theme within the Zienkiewicz Institute. So for those of you who don't know what the Zienkiewicz Institute is, this is one of these kind of umbrella organisations trying to coordinate and provide opportunity for discussion, research collaboration across the faculty in data, AI and modelling. It's kind of built upon the successes of the former Zienkiewicz Centre for Computational Engineering, obviously taking the name of our famous Professor Zienkiewicz, who I'm sure everybody in this room knows a little bit about. The Institute is split into these 5 theme areas, and we thought it would be a good idea to have what we're referring to as our distinguished seminars, at least once a year in each of these themes. I think this is the first one, is that right?
Right, yes.
So the first one is in this area of materials and manufacturing. So we've invited Professor Emile, am I going to get your surname right now?
Greenhalgh.
Yeah. Pronounce the G.
Yes,
Okay.
yeah, I think, yeah.
So Emile joined Imperial College in February 2003, where he currently, according to his website, still lectures in material selection, composite design, testing, characterization and failure analysis. And he's the head of the Composite Centre there. Emile obtained his BSc in physics from Imperial College and graduated in 1987, and then worked at Kinetic, conducting research on a broad range of aspects of fibre reinforced polymers. He's published over 100 reports and papers in this field, and under the general theme of his work has been composite mechanics, understanding and predicting of the structural behaviour of composites. Since 2020, he has held the Royal Academy of Engineering Chair in Emerging Technologies. Over the past 34 years, Emile has built up a respected international reputation in composites. In particular, his research is focused on 2 areas. The first is damage tolerance and failure analysis, fractography of composites, and multifunctional composites, or structural power, which is going to be the main focus of today's talk. He has pioneered the development of structural composites, which have led the capacity to store and deliver electrical energy, and leads one of the largest groups in this field. I first came across Emile probably a couple of years ago as part of a UK aerospace research consortium meeting, which I was attempting to chair, where the 11 universities who form part of the Aerospace Research Consortium, of which Imperial and Swansea are both members, got a small slot. Welcome, Arnold. You can relax now. Where all the universities who are part of that consortium got to present a little bit of their work, kind of that feeds into the problem of sustainable aviation. And it was a fascinating session. But I remember when Emile gave his talk, thinking to myself, goodness me, I didn't know that was even possible. And if you can get that to work, that is genuinely transformative. And I'm sure there's a big if there.
Oh yeah, for sure.
Which is we're going to get covered, I'm sure, to some extent in the talk today. Possibly more importantly than any of that is that Emile is a season ticket holder at Tottenham Hotspur. So we commiserate you on the result last night.
I don't know
you
if
were
it's...
there at the match.
I was, yeah. I might be a bit hoarse from that.
You're in safe hands today.
Oh, that's
so
good.
let's give a big Zienkiewicz Institute welcome to Professor Emile Greenhalgh.
Great, thank you. Could I turn the lights down a bit just to get the images working? Can you all hear me okay? I wasn't sure if the microphone's working. Yeah, cool. Okay, well, thank you for this opportunity to talk about my research, and I think you're going to find it very interesting what we're trying to achieve with this area. Just to sort of focus on my background a bit. So I am from a traditional composites background. I worked a lot on failure and damage in polymer composites, and then moving to Imperial, I moved into more multifunctional materials and nano-reinforced materials. And as you'll see, the sort of development of multifunctional materials is quite dependent on the development of nano-reinforcement, carbon nanotubes, graphene, things like that. They allow us to have these multiple functions in the material. And so we came up with this concept, I think in about 2003, 2004, we started developing this area and came up with some prototypes. And it's now taken off. There's a lot of interest in what we're trying to achieve, this idea of structural power materials. So this is a material that does 2 things simultaneously, 2 very distinctly different things simultaneously. So I now have this Chair in Emerging Technologies funding from the Royal Academy of Engineering, which has given me 10 years to actually mature this technology. And so the aspiration of what I'm trying to do is get this technology industrialized, get industry to take this up and take it forward. But as you'll see, there's some tremendous challenges we've got to try and address. And in fact, a lot of the research up to this point has been trying to work out what are the questions we should be asking with this work. So let me first introduce you to the team. I lead all the work in the group, and my background is mechanical aspects of composites, polymer matrix composites. But one of the challenges in working in a multidisciplinary area, multifunctional area, is that you need to bring in people that are from completely different backgrounds. So I have colleagues that I'm working with. Anthony Kersenak is an electrochemist working on batteries and fuel cells. And then my colleague Milo Schaffer is an expert on nanomaterials, particularly nanocarbons, and using those materials both in electrochemical aspects and in mechanical aspects. Emiliano is his background is in nanomaterials again, but particularly thermoplastic materials. And then Ajit Panesar, some of you may know, he works on additive manufacture and also modeling techniques, so topology optimization, aspects like that. And as you'll see, modeling is going to have a really important role in trying to take this technology forward. And we have a number of researchers. Sang Nagayan works on multifunctional design, and then we have a number of PhDs that are working on various aspects. Ximing's working on the modeling, and I'll show you some of her work a little later on. Emily is developing on structural batteries. Elias is working on thermoplastic electrolytes. So I'll talk a bit about the idea of the issue of the electrolytes, and then encapsulation is being covered by Odysseus. So let me give you the sort of motivation for what we're trying to do. So you'll hear a lot about multifunctional materials. There's a huge area of work on having materials that have electrical and magnetic properties, for instance. But what we're particularly interested in is structural materials. So these are materials that carry mechanical load, which we've imbued with a second, quite different function. So this idea of structural power that I'm going to talk about, but there are also applications with sensing. So having a structural material that can sense its environment. Self-healing materials, this work at Bristol. Actuation, so materials that are structural materials but can also actuate under stimuli. And in even energy harvesting. So these are a range of materials that are starting to get interest. So rather than just having this inert structural material that all it does is carry mechanical loads, we're trying to develop a material that has added functions. So it's more efficient use of those materials. So what I ought to reinforce first of all is that we're really going beyond this idea of smart materials and smart structures. So there's a lot of work that's been going on for decades of embedding sensors or embedding batteries into structures. So for instance, this is some really nice work that's been done, the US Navy, been going on for about 15 years or so, where they've been looking at embedding lithium-ion batteries into aircraft structures, these are UAVs, and looking at that as a way of making more efficient structures. So this idea of embedding devices, embedding batteries into a composite structure is actually relatively mature. But what we're doing is really going beyond that. We're not trying to embed a structure. We're not assembling a product out of a monofunctional structure and a monofunctional battery. We're actually trying to imbue the same material to do two things simultaneously. So for instance, the carbon fibers that we use within our material, they carry structural loads. These are aerospace grade carbon fibers. But those same carbon fibers have lithium ions intercalating into them and out of them to add a battery function. So the technology and the challenges with this are much more immense than for just embedding a battery, for instance. But the rewards from doing this are enormous, and I'm going to sort of elaborate on that in a minute in terms of what achieving this idea of structural power materials is going to mean in terms of our day-to-day lives. But to give some context to what's really driven us this way is this whole issue of sustainability and the issue of energy storage and electrification of transport. So if you're looking at an electric car, the issue you have here is that you have a car that has a number of batteries in, but you need to put more and more batteries in to actually improve the range of the vehicle. But adding more batteries adds more mass, so you need even more batteries to be able to do that particular journey. And so, for instance, if you double the weight of the car by adding more batteries, then it actually, sorry, let me take that back. If you want to double range of the vehicle, you can achieve that by the same amount of energy by halving the weight of the vehicle. And so things like Tesla cars, for instance, about 25% of the weight of the car is actually the batteries. So you're expending 25% of your energy just moving the batteries from A to B. So that in itself is really not very efficiently using these materials. It's parasitic weight. In aerospace, this is even more of a problem. So there's been a really big drive in aerospace to go for this idea of a net zero aircraft, a long-haul passenger plane that's not using any aviation fuel by 2050. So the challenge we have there is that if you're using kerosene in an aircraft, about 30 kilograms of kerosene is required for each passenger. If we use batteries and using current battery technologies, which have an energy density of about 250 watt-hours per kilogram, you'd need 1,000 kilograms of batteries per passenger. So that's really just not feasible. So if you look at the conventional electrochemistry sector, they're really trying to push forward the energy densities of their batteries. And I've got a graph demonstrating this in a moment. But the issue with enhancing energy density is that you run into sustainability issues, you run into longevity issues. A lot of these very high energy battery technologies have relatively short lives. And there's also the issue of safety. So aerospace is a very conservative industry. If you try and get a new material onto an aircraft, you have to go through a lot of steps to demonstrate that it's airworthy. So really, we kind of felt that we need a radically different approach to how we store electrical energy on vehicles. And so instead of having that parasitic weight of the battery, why not use the structural material to actually have an intrinsic ability to also store the energy? So you won't need batteries. Your body of your car, the casing of your phone would store the energy that you need for use. And so we worked very early with Volvo with this concept, and they were very keen on this idea, and we've gone on to demonstrate that this technology is feasible. And there's a lot of synergies here in terms of the sciences. Although we're bringing together electrochemistry and composite mechanics, which are very different fields, there's a lot of parallels. So for instance, in electrical energy storage, carbon is widely used as one of the electrodes, or both of the electrodes in some instances. And in structural applications, we use carbon fibers. So immediately there's some synergy there. There's also this issue that carbon fiber composites that we use in aircraft structures are laminated structures, while batteries, again, are laminated structures. So we thought there's some synergies there that we could try and exploit with this technology. So let me share with you our aspiration for what we hope this technology will achieve. So first of all, as with any sort of lightweighting technology, the idea that you could have a material that does two things simultaneously is going to give us lighter vehicles, it's going to give us more spacious vehicles. So what we're trying to convey here, for instance, is that you no longer need this big pack of batteries in the car, there's a lot more space in the vehicle. So what we're showing here is you're charging the vehicle. So in lots of applications, this is going to give us lighter weight, reduced volume, more spacious applications. But we sort of thought there are things here that this technology is going to offer beyond those sort of conventional things that we think about in engineering. So one aspect we recognized is that a lot of products, particularly portable electronics, the actual form factor of that, of your phone, for instance, is actually dictated by the battery. So in a phone, for instance, half the volume of your phone is the battery. So if we could now get rid of the battery and using the casing of the phone, which is a structural component, but imbue that with the capacity to store energy, you could now have phones as thin as credit cards because you no longer have to think about where you put the battery. So that was something that we thought would be very attractive from a sort of consumer point of view, that suddenly it opens up this space of you can make very slender devices. But as an aerospace person, I was immediately thinking about what can we do in aerospace with this. And so where we started to recognize was that at the moment for aircraft, you have hollow wings. And the reason you have hollow wings is because you need to store the fuel there, be it kerosene or batteries. That's all stored within the wings. But now if the structure of the wing itself or the fuselage stored the energy, you wouldn't have to have hollow wings anymore. So you go to very thin wings, and so therefore you reduce drag, you improve the efficiency of the vehicle. But if you start moving to thin-winged aircraft, you run into air elasticity problems. So the whole aircraft would need to look different. You'd have to start to look at these box wing type configurations, for instance. And so one thing we recognize with this technology is that this is not something that we can just retrofit onto an existing product. This is going to need a sort of blank sheet of paper. It's such a fundamentally different way of using structural materials that you have to rethink everything from the blank sheet of paper. So as we started to think about how we could use these materials, what we started to see was that it offers localization of power storage, energy storage. So you can actually, rather than having the power source as remote from the actual usage of that source, you have an opportunity to bring everything closer together. So for instance, in the aircraft cabin, when you're sitting on your seat watching your entertainment screen, the energy that's driving that is actually coming off the engines of the aircraft. And if you took away the panels in an aircraft, you'd see enormous looms of wiring. So we thought, what about if we actually made the floor of the aircraft cabin out of our material, and then that would then power these seat back displays and the USB ports that we have on the aircraft. And I'll show you in a minute a study that we've done that demonstrates this offers a huge weight saving. But this is something we've recognized with this concept, that it offers an opportunity to localize where you store your energy for a particular application. And then kind of in the wider context of thhow we started to think about how can this go beyond transportation. And so one thing, sorry, how do I get rid of that? One thing we started to think about was infrastructure. So where you're looking at using solar panels on your house, for instance, at the moment you have to have a great big bank of lead acid batteries in your basement to store all that energy. But what about if you actually made the bricks of your house into batteries? So the building, the walls of the building would actually store the energy that you capture with the solar panels. So this is where we saw this technology going. So this is all the aspiration. We're nowhere near achieving these things yet, but we're trying to think about where could this technology take us if we overcome the challenges. And I'm going to talk a lot about what are the challenges with this technology. So let me focus on that cabins application that I spoke about. This is a paper that we published 2 or 3 years ago where we actually looked at, if we considered an aircraft, an A220 aircraft, and we thought about using the floor panels to store the energy, we started to think about what's the sort of levels of performance that we would achieve in the next 5 years or so. So we chose a modulus for the laminates of about 28 gigapascals, and we chose energy and power densities of 144 watt hours per kilogram, so that's a sort of almost half of that of a conventional battery, and a power of 29 watts per kilogram, which is sort of akin to what you get with a conventional battery. So those of you who are not electrochemists, these are 2 parameters that are often used to define energy storage devices. The specific energy is essentially telling you how much energy you can store per kilogram of material, and the energy is in watt hours. And the specific power is how quickly you deliver that energy. So that's watts or kilowatts per kilogram. Okay, so taking those numbers, we started thinking about redesigning the cabin, looked at all the electrical systems, the electrical demands on that system, and we identified that if we took an A220, put this system into the vehicle, using those performance targets, we'd get a weight saving of 260 kilograms of weight per aircraft. That was equivalent to about 500 litres of space saved. And we then translated that into CO2 reduction. So for that vehicle, it would result in 280 tonnes per year of CO2 reduction. And that's about equivalent to 1% of the annual CO2 emissions of a single A220 aircraft on its sort of typical flight schedules. So this was very attractive, and we, as I'll show you, we think cabins is one of the early adoption routes that we see for this technology. We've also done some other studies trying to understand how this technology could be applied to other areas in aerospace. And what we've been trying to do here is what are the target performances we need to achieve in our materials to actually offer a benefit. And that's helping us identify what are the routes of we need to take this technology. So there's a lot of interest at the moment in these types of vehicle, these autonomous air taxis. So the idea is that you could take one of these air taxis to fly from City Airport, which is in the east of London, to Heathrow, which is in the west of London. And if you took a taxi, that would probably take you about 2 hours. But if you flew, it would take you about 15 minutes. So these air taxis hold about 4 people. They don't have a pilot. It's all autonomous. And so various companies like Vertical Aerospace and Airbus are developing these types of vehicle. These are fully electric vehicles, and the challenge with these vehicles is that the battery technology is not there yet in terms of allowing them to have a significant range that's useful. So for instance, the City Airbus vehicle, this is probably a previous incarnation of the development of this vehicle. That has a range, or an endurance of 15 minutes with the batteries they're using at the moment. So we started to think about, if we took the batteries out and we replaced the structure with our material, what benefits could that offer, and what levels of energy density do we need to achieve? And so this is illustrated here, where we're showing for two different types of sources of energy: the conventional batteries, which is the black line, and using structural power material, which is the red line. And this is showing the relationship between endurance of the vehicle in minutes and the specific energy of the power source. And so the take home from this is that if you go for a fixed amount of energy density for your power source, by using structural power materials, you double the range of the vehicle. To put that another way, if you want to fly from London to Manchester, which is 240 kilometres, the conventional batteries would need to have an energy density of about 370 watt-hours per kilogram. And that's not a level that we're going to achieve in the next probably 5 or 10 years or so. For structural power material, you need less than half of that, 170 watt-hours per kilogram, which we haven't achieved yet, but it's sort of within reach. So the attraction in this technology is that it's something that actually will help us achieve electrification of transportation without needing the astronomically high levels of energy density that we need for batteries to achieve that. But let me focus on that a bit in terms of where things are with conventional batteries. Because you read a lot in the newspapers about new battery technologies coming out with horrendously high energy densities. So this is showing you a graph of all the different types of battery chemistries that are evolving and the ones we currently use. So things like lithium ion, for instance, you're familiar with. And this is showing you the specific energy, so how much energy it stores per kilogram, but also the energy density, so how much energy it holds per litre of material. So just to put that in context, for a Tesla car, sits at about 280 watt-hours per kilogram is the pack energy density. There's lots of these new battery technologies like lithium sulfur, lithium air, so this gives you an idea as the sort of levels of performance that those offer. However, if we want to go to a fully electric airliner, those batteries would need to be up here. So if we wanted to have a replacement for the A320, for instance, to fly from here to Greece, you would need to have an energy dense, a specific energy in excess of 1600 watt hours per kilogram. And we're currently at 280 watt hours per kilogram. And to give you a bit more context here, if I had a piece of TNT, that has an energy density of 1160 watt hours per kilogram. So we're trying to persuade the aircraft industry to have a block of material which is even more energetic than a block of TNT. So this is really putting into context the challenges associated with going for a fully electric, conventional battery-powered airliner. So we thought, why don't we explore what happens if we use structural power material in this context? And so what we started to think about was, what about if we had an airliner which was a hybrid of conventional batteries and structural power material? So the wings, the body of the aircraft would store the energy, and you'd had to add some more batteries to give you all that energy you'd need. So this graph is kind of capturing what we found with that. So we looked at different energy levels for our structural power material, and then these lines indicate different energy densities for different battery technologies. And then the horizontal axis showing you the mass of conventional batteries you'd need to allow that airliner to fly from here to Greece, for instance. So for example, you could use, say, 17 tons of conventional batteries at 700 watt hours per kilogram, which is, almost 3 times higher than the conventional technology, but certainly not in that sort of really high 1500, 1600 that I mentioned earlier. And structural power material that's at about 300 watt hours per kilogram. So what we were starting to see with this technology, if we can get it up to the higher energy levels, it starts to become an enabler for fully electric aircraft. But those of you working in aviation recognize that the reason that we've had this sort of change now to hydrogen is specifically because of that issue of the battery technology. But what we see with structural power is that it doesn't necessarily have to be used with conventional batteries. It could be hybridized with hydrogen power. So the idea, for instance, is that you'd have a hydrogen-powered propulsed aircraft that powers the engines, but then you'd use structural power materials to run the cabin and things like that. Okay, so let me talk a bit about the sort of where things are in terms of structural power materials and focus in on the technology that we're working on. So if you talk to an electrochemist, they'll show you this type of plot, which is a Ragone plot, which is showing you the relationship between specific energy and specific power, or it could be energy density and power density. So if you're looking at volumetric terms. And these are the different types of devices. So batteries have high energy density. Sorry, let me put this into a pointer. So batteries have high energy density, but they are very sluggish because they work by chemistry. There's a chemical reaction going from charged to discharged. And so thermodynamics starts to become very important for batteries. So the batteries, although they can store a lot of energy, and fuel cells are even worse, even better in terms of how much energy they store, they're very slow at delivering that energy. The other end of things are capacitors, so electrostatic capacitors, the sort of thing you might have used at school. Those deliver energy really quickly. They have a specific power in the order of 10 to the 5, 10 to the 6 watts per kilogram. But they can't store very much energy. So those capacitors tend to be used in sort of energy weapons, lasers, where you want to deliver energy really quickly. What we focused on are known as supercapacitors. So supercapacitors are essentially a type of capacitor. So if you might remember from school, the way a capacitor works is you have 2 plates which are a certain distance apart, and the closer you get them together, the higher the amount of capacitance you have, and then the amount of charge you can store is related to the surface area of those plates. So what happens in the supercapacitor is we make that surface area really, really large by making the surface really tortuous. So it's very high surface area. And then the charges are actually stored at the interface between the electrodes and the electrolyte. So rather than being millimeters, they're actually the order of nanometers apart. So by doing that, you can develop supercapacitors which can store